Thank you for watching this presentation. I'm Kyusun Lee from Sungkyunkwan University. Today I'm going to talk about hardware-based demand paging, which aims to replace the conventional software-based demand paging. This is a joint work with co-first author Wenjing Jin and my colleagues at both Sungkyunkwan University and Seoul National University. Demand paging is the core mechanism of virtual memory, which allows multiple processes to efficiently share the physical memory. By loading only those pages that we need, it generates fewer I/O requests, uses less memory, gets faster response, and better supports multiple processes running at the same time. Due to these benefits, demand paging is also utilized in various applications, such as NoSQL application, in-memory MapReduce, and Graph Analytics Act. Traditionally, in an environment where slow storage is used as backing store, I/O time was dominant in demand paging. However, as the performance of storage devices continues to scale, and emerging ultra-low latency SSDs such as Samsung GSSD can deliver a single I/O within a few microseconds, the time spent in the software stack is becoming more and more significant. We performed a breakdown of single page fault to confirm this. When a page fault handling exception occurs, the kernel passes through the kernel I/O stack to request I/O. After device I/O completion, an interrupt is raised and context switching occurs. Then I/O completion and PTE update are performed to wake up the user process by an exception. According to this breakdown, the OS kernel overhead in demand paging is quite substantial, taking about 76% of the device time. Also, page fault handling incurs not only such direct costs, but also indirect costs such as architecture resource pollution. With frequent page faults, the system keeps switching between user and kernel modes to cause a substantial amount of microarchitectural resource pollution. When we measure it using hardware performance monitoring unit, the number of missed events significantly increased and user-level IPC decreased compared to the baseline with no page faults. This is an excerpt from a popular operating system textbook which says, why hardware doesn't handle page faults? The first reason is disk is too slow. Data fetching from disk takes too long, so there's no benefit if page fault is handled by hardware. The second is that the hardware doesn't know the storage layout. Actually, the CPU cannot know how the data is stored inside the disk. However, the first reason is becoming less and less true with emerging low latency SSDs, and our proposal solves the second problem to make hardware-based demand paging viable. For a clear comparison with our scheme, let's first look at operating system-based demand paging. When an application accesses any virtual address, MMU scans page table and raises page fault exception if it misses for the operating system to fetch the requested page from disk. In our scheme, at a page miss, MMU doesn't raise an exception. Instead, the CPU fetches the requested page directly from disk. This concept looks quite intuitive and efficient, but there are several challenges that need to be addressed to accomplish this. First, since the CPU doesn't know the storage layout, we expose the storage layout to the CPU via LBA augmented page table. Here, LBA is a logical block address, which means the sector number of the page in the disk, and the location in the file can be specified with LBA. Second, the CPU needs a method to directly access the device, and we have provided this by introducing a new architecture component called the Storage Management Unit. Finally, we need to handle operations that cannot be handled by the CPU, and we propose OS support for hardware-based demand paging by extending system calls and using kernel threads. In our scheme HWDP, no exception needs to be raised in common cases. Therefore, the latency of a page fault can be reduced, and the architectural resource pollution can also be mitigated. In the rest of the talk, I'm going to present details about architectural extensions and operating system supports for HWDP. Then I'll show the evaluation results. The LBA augmented page table contains LBA information and it can be accessed from the CPU via MMU. The x86 architecture used in this work has a 4-level page table as shown. In the conventional system, the present bit in the PTE indicates whether the page exists or not. If there is a page, the page frame number is written in the PTE, otherwise all the other bits are ignored. In our LBA augmented page table, we used one unused protection bit as an LBA bit to determine whether the PTE contains an LBA or not. Also, we extended the MMU to check the LBA bit together during a page table scan to expose it to CPU. The LBA augmented PTE includes socket ID and device ID to multiple devices over multiple sockets. CPU can identify the correct block device in the system with these IDs. Next, we'll see how the LBA augmented PTE is set in hardware-based demand paging. If MMU detects LBA augmented PTE during the page table scan, it requests an I/O operation directly through SMU. After page mishandling is done, PFN is written in PTE and the present bit is set, but LBA bit is still maintained to 1. This means that the page miss has been handled by hardware, but the page-related OS metadata is not updated yet. Later, when this page-related OS metadata is updated, LBA bit becomes 0 and PTE becomes the conventional PTE with resident page. The SMU is a key architectural component for HWDP. It consists of 2 parts, page mishandler and NVMe host controller. The former handles page misses issued by cores, and the latter handles storage device specific I/O control. In HWDP, MMU requests the page mishandling to the SMU corresponding to socket ID in PTE. At this time, MMU delivers PTE address, device ID, and LBA together. Before we move on, one question here is how to synchronize page miss in hardware. Because there is no page cache in SMU, so duplicated page mishandling can occur on the same page in a multi-threaded environment. To handle this problem, page mishandler maintains the page miss status holding registers, or PMSHR, which tracks the status of outstanding page misses. So multiple page misses to the same page can be coalesced through PMSHR lookup with PTE address as the key. If PMSHR lookup fails, one unused PMSHR entry is allocated and page miss information is written to the entry. After that, a physical page frame is allocated to fetch data. A page is allocated from the free page queue, which has been pre-configured in memory. Each entry of this queue is a pair of the page frame number and DMA mapping address to the page, so the page can be used directly without any additional work in the SMU. In the free page fetcher, a few free pages are prefetched into SMU in advance, which takes the latency of page memory allocation from the critical path so that I/O can be requested quickly. The page frame number of the fetched page is updated in the PMSHR entry. Then, I/O information, including LBA, is passed to NVMe host controller to generate an I/O request. When page mishandler receives a notification of I/O completion from the NVMe host controller, the page table updater updates the PTE. The LB field of the PTE is changed to page frame number and the present bit becomes 1. Finally, the PMSHR entry is freed and SMU broadcasts a message to notify cores of completion of page mishandling. In order to enable the NVMe host controller to directly handle I/O in compliance with the protocol, the operating system configures NVMe queue pair to be used by SMU and registers queue pair information such as queue addresses in the NVMe queue descriptor registers. Therefore, the NVMe host controller can request I/O and confirm I/O completion via registers directly. For I/O completion, our scheme disables interrupt to avoid OS intervention. Instead, the NVMe host controller monitors all memory write transactions from the PCIe root complex via snooping the memory address of completion queue. Next, let's talk about the operating system supports. First, operating system provides fast file mmap feature, which is a new interface to utilize our HWDP. The operating system allocates a region of memory mapped file to use HWDP. Also, it marks the area so that associated metadata can be updated lazily. Currently, we only support files that are not shared by multiple processes, as our scheme can handle a shared page among multiple processes correctly. When FastFile mmap is called, it constructs LBA augmented page table for entire area. If the page exists in page cache already, the page is retrieved and populated in the PTE. Otherwise, it receives the LBA from the file system and writes it to the PTE. LBA bit is also set. Whenever a page miss is handled by SMU, its associated metadata should be updated, like inserting a new page into the LRU list. Our approach is to introduce a kernel thread called KPTED that runs in background, scans page tables, and updates metadata when it finds PTEs whose page miss is handled but metadata is not synchronized. Since SMU does not clear LBA bit after page mishandling, KPTED can easily recognize them using LBA and present bits. However, the cost of periodic scanning is huge, so we need to reduce the page table scanning overhead. Our solution is using additional bits in upper level page tables. Hence, the upper level entries also have an LBA bit, and the bit is set when the leaf page table has a PT whose page miss is handled in hardware. Therefore, whenever KPTED scans page tables, it can skip a bunch of PTs when an LBA bit of upper level entry is clear. To preserve this semantic, KPTED checks LBA bit of upper level entry and clear the bit when it goes to the lower level. The next OS support is to fill free pages in the free page queue. The first way is synchronous page refill. When the SMU fails to allocate a page during page mishandling, it raises a page fault exception. The OS page fault handler handles the page fault and refills the free page queue by allocating free pages from the OS memory allocator. However, this synchronous refill causes page faults, which are events we want to minimize. To accomplish this, we introduced another kernel thread called KPOD that periodically refills the free page queue. We empirically found that using the KPOD can reduce up to 78% of page faults caused by the lack of free pages in the free page queue. Let me summarize the conventional OS-based demand paging and our hardware-based demand paging. In OSDP, file system, block IO stack, and OS metadata operations are on the critical path at every page miss event. In HWDP, however, all system operations are batched at the beginning. Block IO stack operations are replaced by SMU. OS metadata operations are detached from the critical path and handled in the background. As a result, the page mishandling latency is greatly reduced and no page fault exception occurs in the critical path. Now the evaluation. Our architectural proposal requires thorough evaluation not only in microarchitecture level, but also in end-to-end system level. Since it is difficult to measure performance of long-running workloads with a cycle-level simulator, we implemented our scheme entirely in software and ran the prototype on a real x86 machine. In addition, to estimate the performance when our scheme is implemented in hardware, we adjusted the throughput results as follows. First, we measured the delta of single page mishandling latency between the two environments. Then we adjusted the throughput results by subtracting the delta to those that page misses are handled in hardware. First, the timeline of actions during a single page mishandling in our scheme. When a page miss occurs, MMU sends a page mishandling request to the page mishandler via an on-chip bus, which takes 1 cycle or 0.36 nanoseconds. And the page mishandler first looks up the PMSHR, which is a content addressable memory or CAM. It takes 5 cycles, which is similar to L1 cache access time. Upon a miss on the PMSHR, the page mishandler retrieves a free page from the prefetch buffer, which takes one cycle. After that, the SMU updates the PMSHR entry using the new page frame number. Then it sends an IO request to the NVMe host controller. At the same time, the page mishandler accesses the free page queue in memory to prefetch a free page for the next page mishandling. Then NVMe controller writes the NVMe command to memory. It takes 77 nanoseconds, which is the most time-consuming operation in page mishandling. Then it rings the doorbell, which takes 1.6 nanoseconds. After the device I/O time, the completion unit takes 2 cycles to check the I/O completion, then percolates the completion upward to the page mishandler. Then it writes the CQ doorbell register. At the same time, the page table updater in the page mishandler reads and updates the PT, PMD, PUD entries through several memory accesses. We observed that these accesses rarely miss the CPU's last level cache, so we assume these operations take 97 cycles, which is the time for 3 last level cache reads and writes. Finally, SMU notifies MMU including bus access and completion checking, which takes 2 cycles. This graph shows the latency comparison between OSDP and our HWDP. Our scheme greatly reduces the latencies before device I/O operation and after device I/O operation because all the operations are performed not in software but in hardware. The single page fault handling latency is reduced by 43%. We tested our scheme with various applications. This graph shows the throughput improvement by our HWDP over OSDP. FIU and DBbench on RocksDB showed the biggest throughput improvement by up to 57% since they have uniform read-only access patterns. YCSB workloads showed less throughput improvement since they have more realistic GPN access patterns. YCSB-C, which is a read-only workload, showed the biggest throughput gain by up to 27%. The performance gains are reduced in other workloads since they are a mix of read-write or read-update. Because the latency reduction by our scheme is static, a longer read latency shows a less performance gain. Also, as the number of threads increases, the performance gain is slightly reduced on several workloads. We believe this is due to the increased contention in page tables and PMSHR. Because of our software-based model is organized not into registers, but into memory table, which incurs cache line contention with many threads. We also verified how well our scheme suppresses architectural resource pollution due to eliminating page faults. We measured the number of branch and cache miss events and user-level IPC of the YCSB-C workload. The workload showed 25% of throughput improvement and its user-level IPC was also increased by 7% due to the reduced miss events. Now the conclusion of this talk. Scaling SSD performance demands new directions because of relatively increased overhead in software. We extend the conventional CPU architecture to support demand paging mostly in hardware. Proper OS supports also accompanied to utilize the proposed hardware efficiently. Our scheme successfully detaches OS involvement mostly from demand paging. This results in increasing demand paging performance as well as improved user-level IPC. Our performance evaluation demonstrates the proposed scheme improves the throughput of realistic workloads by up to 27%. Thank you for watching this presentation again, and if you have any questions, please post your questions on our discussion board.